All right, let's go ahead and do some mean value theorem today. If you have your blue books, it's on page 65 in the blue book. If not, go ahead and either take your own notes or go ahead and print off the website, the page that you need. Skip the goal problem for today. Let's go ahead and jump into number one. Okay, if we're doing mean value theorem, a lot of kids will get this confused with the intermediate value theorem that we talked about previously. So let's go ahead and review what IVT is. Number one says, what is IVT and what does it show? And what I want you to think back to is our airplane problem, right? Where we went from an altitude of 0 meters to 10,000 meters. And the question was, or what IVT showed us, is that we would hit 8,623 meters at some point along the interval. And we had to reach a couple of requirements. First off, that the function was continuous. And then we had a certain way that we were going to write our answer to be 100% sure that we were guaranteed to hit 8,623 meters. But the point was that we went from 0 meters to 10,000 meters, and that we would hit at some point along the way 8,623 meters. Okay, we were all on the same level with IVT. It was meters, meters, and meters. Now, we could even done something like, I don't know, if you're driving your car, right? And you are on the interstate and you're driving 65 miles an hour because you're following the speed limit. So if we had an initial miles per hour of 65 miles per hour, and we're exiting off of onto a ramp, and we come to a complete stop, which is 0 miles per hour. If we go from 65 miles per hour to 0 miles per hour, are we going to hit, let's just say, 45 miles per hour along the way? The answer is, oops, got to go the other way. Yes, right? Because 45 miles per hour is less than 65 miles an hour, and it's greater than 0 miles per hour, and we're going to be guaranteed, because we're continuously driving our car over the interval, because it's miles per hour, miles per hour, miles per hour, IVT could guarantee that we're going to hit 45 miles per hour. Okay, we could do the same thing with some sort of an acceleration as well. But the idea here, or the key thing about IVT, is that it's the same level. Meters, 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 miles per hour, miles per hour, miles per hour, and we could even do an acceleration if we wanted to. Now, mean value theorem is going to be a little bit different than that. Let's start to explore that a little bit here. For number two, number two asks us to consider y equals x squared, and we're computing the average rate of change over the following intervals. Now, I'm only going to do A and C here. I'm going to need a little bit more space, and I don't want to take up all of your time here. But let's go ahead and compute the average rate of change here. Remember, average rate of change is just slope, so I want f of 2 minus f of 0 for letter A, all over 2 minus 0. And if my function is x squared, 2 squared is going to be 4, minus 0 squared, which is 0, all over 2 minus 0, which is 4 over 2, which is 2. All right, let's go ahead and do the same thing over here for letter C. Same thing, right? F of 2 minus f of negative 2, all over 2 minus negative 2. We did 2 squared is 4. Negative 2 squared is also 4. All over 2 minus a negative 2, I think, is positive 4. Oops. Our average rate of change here is 0. So now we're doing an average rate of change here. We're starting at a y, and when we do an average rate of change, right, this is going to be, for instance, if y was in terms of meters, this could be meters per second, right? We're dropping down a level. All right, so let's take a look at number 3. Number 3 says, is there an instantaneous rate of change, right? Think derivative, IROC, over the previous intervals that will equal the average rate of change. So I'm going to see if there is a derivative of our function that is going to equal what the average rate of change is. Okay, and then we'll do the graph part here in just a second. Again, since we didn't do b up above, we're not going to do b down here. Let's go ahead and do the instantaneous rate of change, right? Instantaneous rate of change, actually it's not f, we can call it y prime, is 2x. Now, if I want to know, is there an instantaneous rate of change, or is there an input for the instantaneous rate of change that's going to equal this output? So let's go ahead and say 2 equals 2x. And if we divide by 2, x will be 1. Let's go ahead and actually do a graph here to support this, and let's see if I can put this over here. Okay, I'll draw a graph. We end up with our parabola here, and we're looking over the interval from 0 to 2, right? Now, our average rate of change, that's just the slope through the point 0 or the input 0 and the input 2. So what we're really finding is the slope of that line right there. Now, from a graphical standpoint, we want to be able to see if there is a tangent line that has that exact same slope over the interval from 0 to 2. And we know it's going to happen at x equals 1. And if I was to draw the tangent line in, it would have the same slope at x equals 1. Now, this graph is not great. I should have spaced it out a little bit better, but I think for letter C, it'd be able to help us out. Same slope means parallel lines, and we have an instantaneous rate of change, or the slope of a tangent line here, that is going to equal the slope through the endpoints. All right, let's jump over to C. Let's see if we can do that. I think maybe the slope of 0 up here is going to actually help us out. We still have y prime equals 2x. And now we want the slope of our tangent line to be 0, so we want y prime to be 0, equals 2x. Again, dividing by 2, x will be 0. All right, so now let's go ahead and draw this one. I think this one makes a little bit more sense to us, hopefully. Okay, I'm going to draw my parabola. Hopefully it's a little bit better picture this time. Positive 2 will be out here, negative 2 will be over here. And it makes sense, right? That if we are the same distance away from the vertex of the parabola, we end up with a slope of 0. Now, we want the input, in this case x equals 0, that has the slope, which is also 0, and hopefully it makes a little bit of sense, right? Hopefully it makes sense that this would be a slope of 0 for our tangent line. Okay, we have a minimum value, right? We changed from decreasing to increasing, so we would have a minimum value at that point. All right, so let's go ahead and formally talk about it. All right, mean value theorem. Again, we're assuming that a function is continuous on our interval, which is the same as the IVT, right? And we're differentiable now on the open interval. Now we're going to say that there exists a C. This is an input, right? There is an input inside of that interval so that the derivative equals the average rate of change. So we can call this the instantaneous rate of change, IROC, equals the average rate of change. Okay? Now, the one thing I want to point out here is that this is all talking about a derivative, right? We're using a function, right, a y, to show something about y prime, a level below. And that's what differentiates it from what we had talked about with IVT. Remember, IVT compared the same level, meters, 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 miles per hour, miles per hour, miles per hour. This one, we're going to end up taking a look at a derivative, right? So we're dropping down a level. And that's the big difference between IVT and MVT, okay? Or one of the differentiators that you can take a look at and say, okay, this is how I can say MVT, this is how I can say IVT, okay? We drew some graphs up above, so I'm going to skip that for now. Let's go ahead and turn the page. Let's work one of these problems. Number 5. It says find a C value, find an input, right? We want to find an input over the interval from 1 to 9 for our function f of x equals the square root of x that satisfies the mean value theorem, right? MVT. So we're going to do a rock equals I rock. I want to find that value of the input where the derivative equals our average rate of change. So let's go ahead and do this. Average rate of change is f of 9 minus f of 1 all over 9 minus 1. Okay, we're taking the endpoints and finding the average over those endpoints. So, and we want to set that equal to the derivative of f of x. And again, if you need to think about this as x to the 1/2, I think it's going to be, let's do it over here actually, f prime of x would be 1/2, equals x to the negative 1/2. And x to the negative 1/2, we can throw it into the denominator and rewrite it as a square root. So I'm going to call it 1 over 2 root x. That should be x. All right, let's go ahead and compute our AROC on the other side of the equation. If I plug 9 into my original function, the square root of 9 is 3, minus square root of 1 is 1, all over 8. So average rate of change equals instantaneous rate of change. Let's see, 3 minus 1 is 2, so 2/8 can be reduced to, 1/4? Equals 1 over 2 root x. Cross multiplication, 2 root x equals 4. Divide by 2. The square root of x should be, 2. And if I'm going to square both sides here, right, to get x by itself, x should equal 4. So the value, a c, right, an input, the input where the average rate of change equals the instantaneous rate of change, the c value is going to be 4. Okay, and if it asks for a justification, we could say by MVT, right? All right, let's go ahead and do one more example here. Let's do letter B actually. Got our function here. We're not going to do C, we're not going to do A. Let's go ahead. We are finding a C that satisfies the MVT, satisfies the mean value theorem. So go ahead and, if you need to, do your calculator here. I'm going to do an average rate of change equals an instantaneous rate of change. All right, so my AROC equals my IROC. So my average rate of change is going to be over the interval from -1 to 1. So I want y of 1 minus y of -1 all over 1 minus -1, average rate of change. And I want to set that equal to my IROC, my derivative. Let's see, x squared, let's see, that'll be what, just x, minus 2. Average rate of change, instantaneous rate of change. Let's see, if I plug in 1, this is going to get messy. I've already done it in my calculator. I think it simplifies to -5/2 minus, plugging -1 in, I think you'll end up with 7/2 there. All over 1 minus a -1 is 2. And -5/2, that's a 5. -5/2 minus 7/2 is what? -12/2. And -12/2 I think is -6/2 equals x minus 2. And -6 divided by 2 is -3 equals x minus 2. So the x value, when we add it over, will become -1. And -1 falls in our interval from -1 to +1. So the c value that we want here is -1. And again, if there was a justification step, we could say by mean value theorem. All right. Now, the problems that you're going to do, I think, are 7, 8, and 9 from the notes book, from the blue book. If you have any questions on those, please send those to me. You're going to start to take a look at these from a little bit different perspective. So if you have questions, let me know.